Welcome to this explainer. Okay, let's jump straight into it because today we're looking at something that is fundamentally, and I mean permanently, altering the hard sciences. For decades, artificial intelligence in chemistry was kind of treated like a fancy calculator. It was just this peripheral tool crunching numbers in the background. Well, looking at the landscape today in mid-2026, that era is entirely over. AI isn't just assisting chemists anymore, it's actively proposing the exact molecules that could cure diseases and the materials that could capture carbon. But we have to ask, how much of this is just hype and how much is reality? Today, we're going to separate the demonstrated results from the wild projections.
Okay, let's dive into this. Here is our roadmap for today. Part 1, the paradigm shift. Part 2, real-world impact. Part 3, how computers speak chemistry. And Part 4, the critical reality check. Section 1, the paradigm shift. To really understand where we are in 2026, we have to look back at the massive institutional validation that happened just a couple of years ago. I'm talking about the 2024 Nobel Prize in Chemistry. This prize went to David Baker for computational protein design, alongside Demis Hassabis and John Jumper for protein structure prediction using AlphaFold. Now, this wasn't just a pat on the back for a neat piece of software. It was the ultimate scientific establishment recognizing, beyond a shadow of a doubt, that algorithms can solve structural biology problems that had literally stumped humans for half a century. And that leads us to this quote. This is the clearest institutional signal that AI is now core chemistry, not a peripheral computational tool. I really want to emphasize that word, core. For any grad student or working chemist today, understanding how these AI mechanisms function is no longer just optional. It's absolutely essential to the modern scientific method.
Moving right along to Section 2, discovering drugs and materials.
Now, what's really interesting about this is that it's one thing to predict a protein's structure on a computer screen, right? It's another thing entirely to create a physical drug or material that actually changes lives. Enter rentosurative. Developed by In Silico Medicine, this is an absolute landmark milestone of the AI chemistry era. It's the first investigational drug where generative AI was used to discover both the biological target, which is a specific kinase, and the therapeutic molecule itself to treat idiopathic pulmonary fibrosis. And it wasn't just a computational win. In June 2025, Phase 2A clinical trials actually showed statistically significant positive results in patients compared to a placebo. Generative AI didn't just suggest a random molecule, it built an active working therapeutic. But the real shockwave hitting the pharmaceutical industry right now, it's the timeline. Traditionally, the discovery and preclinical phase of a new drug takes around 6 years. With AI, that has been slashed down to roughly 2 to 3 years. That is a massive 30 to 40% reduction in time. And if you look at the lead optimization phase, companies like Accenture have cut that down from 4.5 years to just 1 single year. These aren't just abstract efficiencies on a spreadsheet. We are talking about billions of dollars saved and, more importantly, potentially years of extra life for patients waiting for these treatments.
And this acceleration isn't just limited to biology either. Let's pivot to material science for a second. 2.2 million. Just let that massive number sink in. That is the number of new crystal structures predicted by Google DeepMind's Genome, the graph networks for materials exploration. To put that into perspective, the researchers described it as equivalent to 800 years' worth of materials knowledge. That's essentially fast-forwarding from the Middle Ages directly to today, generated in a fraction of the time. Over 380,000 of these are predicted to be thermodynamically stable, and hundreds have already been independently synthesized in external labs.
Section 3. How computers speak chemistry.
So you might be wondering, how exactly is this all happening? Well, before an AI can predict a miracle drug or a revolutionary battery material, it has to actually be able to read a complex 3D molecule. The most fundamental step here is representation. The algorithm needs a mathematical object. One of the most common ways to do this is using something called SMILES. Essentially, this takes the 3D branching graph of a molecule and converts it into a flat line of text, an ASCII string. Why does this matter? Because once a molecule is represented as a simple string of text, AI can treat chemical reaction prediction just like a sequence-to-sequence translation problem. It's exactly the same underlying architecture that translates English to French, but here it's translating reactant molecules into product molecules.
Let's move to and see how this builds with an even more advanced method, graph neural networks, or GNNs. Instead of flattening a molecule into text, a GNN treats the whole molecule as a network where atoms are nodes and bonds are edges. It uses a super clever process called message passing. Step 1. An atom looks at its direct neighbors and gathers or aggregates data about them. Step 2. It updates its own profile or feature vector based on what it just learned. As this repeats layer by layer, every single atom effectively learns about the entire chemical neighborhood around it. Finally, step 3, a readout function pulls all this atomic knowledge into one master mathematical summary of the whole molecule. It's like a giant puzzle coming together.
Now, the crucial point here is that for these models to be truly powerful, they need a secret sauce called equivariance. In simple terms, if you rotate a molecule in 3D space or just shift it to the left, its total physical energy shouldn't change, right? I mean, it's still the exact same molecule. An equivariant neural network guarantees this mathematical consistency by design. This breakthrough is what allows modern neural network potentials to achieve the accuracy of incredibly slow, highly complex quantum mechanical calculations, but at a total fraction of the computing cost. Basically, it gives us high fidelity at high speed.
Which brings us to Section 4, the critical reality check.
So we've seen the incredible speed, and we've explored the brilliant math running underneath it all. But look, science is absolutely nothing without rigorous skepticism. We have to ask the hard question directly. Is the AI chemistry revolution too good to be true? As of mid-2026, the hype machine has for sure been working in overdrive. So let's peel back the curtain a bit and impartially look at where the AI is actually stumbling in the real world.
Let's start with those widely publicized success rates for AI-discovered drugs. A prominent analysis previously claimed an 80 to 90% phase 1 clinical success rate for AI programs. Sounds amazing, right? But a deeper dive highlights a really critical caveat. Researchers point out that this claim suffers heavily from early-stage selection effects and small sample sizes. If you look at conservative, peer-reviewed data from 2025, there are actually only about 29 verified AI-driven clinical programs. That differs sharply from aggregator figures out there claiming hundreds. We really have to separate projected impact from demonstrated impact.
And this brilliantly illustrates the ultimate bottleneck in all of this. Despite billions of dollars poured into AI drug discovery platforms, as of December 2025, exactly 0 entirely AI-discovered drugs have achieved final FDA approval. 0. AI has miraculously compressed the early discovery and preclinical stages, yes, but the total drug development timelines are still completely dominated by human clinical trials. The algorithm, no matter how fast it is, still has to wait for human biology to run its course.
Furthermore, the foundational models themselves are facing some pretty intense scrutiny. Remember those 2.2 million crystals from Google's genome we talked about? Well, critics in the chemistry community have argued that many of those so-called novel crystals were actually just duplicates of already known structures, which even led to calls for the study's retraction. And over in synthetic chemistry, platforms like IBM RxN sometimes generate entirely chemically nonsensical transformations. They might predict a reaction with super high confidence, but upon human inspection, atoms literally vanish or just appear out of nowhere, which is a blatant violation of the basic laws of physics. The data clearly shows that AI simply cannot be deployed blindly in the lab.
So where does this leave the human scientist? Well, the economic and practical role of the chemist is permanently shifting. The days of endless manual trial and error at the laboratory bench, those are fading fast. Instead, the chemist's job is elevating. It's shifting toward framing the right hypotheses, interpreting these incredibly complex model outputs, and most importantly, providing expert validation and oversight of these autonomous systems. AI is the engine, absolutely, but the human is still very much steering the ship.
Which leaves us standing at a fascinating crossroads as we look toward a future of self-driving labs and quantum computing. AI is automating the laboratory, mapping millions of unseen structures and predicting drug targets in months instead of years. But, as we've seen, it still stumbles on basic physics without human oversight. So as we move deeper into this new era, we have to wonder, will the next world-changing chemical breakthrough be the result of a spark of human intuition or the corrected hallucination of a machine? Thanks for joining me on this explainer, and keep questioning everything you learn.